Okay, so we're going to talk about buffers today. We've sort of briefly introduced them, but not talked about them in detail. So what does a buffer do? A buffer is a system that resists changes in pHs. And that's because a buffer has two parts. It has an acidic part and it has a basic part. And because of that, you can add small amounts of acid and the base part will neutralize it, or you can add small amounts of base and the acidic part will neutralize it. And so there's two ways to make a buffer. In the preparing a buffer video, the way that you're making it is from a weak substance and a salt that has the conjugate of the weak substance in it. That's one way. The other way buffers can be produced is like a byproduct of a neutralization reaction. So the acid and the base react and inadvertently form a buffer system. Okay, so it starts off as neutralization, but then turns into a buffered system, and we'll talk about why. And again, this buffer system is like this idea of a common ion. So we'll talk about what that means in just a second. So if we want to look at just a buffer with the salt. So look at this. We have acetic acid, okay? Acetic acid is a weak acid. Acetic acid exists almost entirely of this guy and very little of those guys. Now, it does ionize a little bit, which is what makes it a weak electrolyte, but the equilibrium lies super far to the reactant side, super far to the left, and so acetic acid does not give us a lot of acetate. So a weak acid alone cannot be a buffer, okay? In order to be a buffer, you have to have an acidic part and a basic part. And what do I mean by basic part? Look, this is an acid, this is a base, conjugate base, right? This guy is its conjugate base. I need both of these parts to be a buffer. The acid alone does not give me enough of acetate to be a buffer. So what you can do is you can plug in a salt that has the common ion. The common ion being acetate. Okay? Acetic acid has acetate and it also breaks down. So what you do is you take a salt like sodium acetate, lithium acetate, potassium acetate, don't care who it's with. And remember, salts, for right now, completely ionize. So salts are giving you all of this and all of this. It doesn't really stay like this, assuming it's a soluble salt. So if you put the salt in with the weak acid, now you have tons of acetate. But the acetate is coming from the salt. It's not coming from the acetic acid. The acetic acid is in there, and then this part of the acid is coming from the fact that you threw a salt in with it. So again, a salt alone can also not be a buffer because you have this conjugate base, but you don't have the acidic part with just a salt in solution. You've got to have both parts to be a buffer. Okay? Now, we learned a couple of ways to find pH. The easiest way is if you know H plus or H3O plus, right? Same thing for now. You can do pH is opposite the log of H. That's one way. Okay? If you know OH, you could find POH because POH is opposite the log of OH. Now, if you don't have H plus or OH and you have what's known as a buffered system, you can use the Henderson-Hasselbalch, and this is on your equation sheet, right? Where pH equals pKa plus the log, the conjugate is on the top and the weak substance is on the bottom. Now, the conjugate on the top is the salt for this buffer. So this is a weak acid and the salt. So when you do like acetic acid and sodium acetate, and you have both parts, okay, this is the weak acid, that would go here. This is the salt. This would have been sodium acetate, okay? And it's the acetate that we care about, so that part would go up here. Now, a basic buffer is possible as well, and all they've done is they've just replaced all of the acidic parts with basic parts. Instead of pH, it's POH. Instead of Ka, it's Kb. And then notice that you have the weak base on the bottom, just like you had the weak acid on the bottom, and its conjugate, or the salt, on the top. Why is this BH plus? Well, because bases accept hydrogen ions, so that's why its conjugate looks like that. Okay? All right. I don't need you to know how to do this, but I am going to do it for you. Where did the Henderson-Hasselbalch equation come from? Now, it's on your equation sheet, so it's just there, but they didn't just like pull it out of nowhere. What they did is they rearranged an equilibrium expression. So I'm going to give you a generic weak acid, and I'm going to write it two ways, okay? This is one way I could write it. Or you can do the shortcut way where they do this. Okay, these are synonymous with one another. One has water, one doesn't. One has the hydrogen ion, one has the hydronium ion. But they're synonymous with one another, okay? Oops, equilibrium, sorry. Okay, and you write a K, so this is some acid, HF, HC2H3O2, HClO, H whoever, okay? Some weak acid. And they write an expression, so Ka equals products over reactants raised to their coefficients, right? Actually, I'm going to move this to the middle so I have room. And I'm going to just write the abbreviated way. It doesn't matter though. All right, and I'm going to assign you the task of isolating the hydrogen ion. So this is just basic algebra. You're going to move the HA up and the A minus down. Okay, so the HA goes here, and the A minus goes down here. So these go away, right? Bye-bye. And now I've just rearranged to find H. Okay, well, what if I want to find pH? What would I do to this term right here? I would take opposite the log of it. Is that right, to find pH? So if I take opposite the log of the right side, I get pH. Well, in math, if you do something to one side of an equal sign, you have to do it to the other. So I have to take the opposite the log of the other side. Now, does anybody know how logs work? You might not. I don't need you to know, but I'm going to tell you. When you log things that are being multiplied, they're actually being added together. So opposite the log of this term and then opposite the log of this term. Well, opposite the log of Ka is pKa. So now we have pH equals pKa. And the opposite sign for this term right here flips your fraction upside down. It means the fraction is going to be inverted. So now I have A minus on the top and HA on the bottom. And it's the log of that number, right? The opposite is what flipped it, but you still have to do the log of it. And when you multiply terms with logs, they're actually being added together. That's just the rule of logs. This is Henderson-Hasselbalch. pH equals pKa plus the log of the conjugate over the weak substance. That's where it came from. They didn't just like pull it out of the sky. They basically rearranged and took logs of both sides. Okay, so what does that mean for buffers? It means you actually could use the Ka expression instead of the Henderson-Hasselbalch equation to determine pH. And I'll show you how in a little bit. Either way is fine. It doesn't matter which way you do it. I just want to have you do the way you feel the most comfortable with. Okay? I just wanted to show you that Henderson-Hasselbalch equation, which is the equation for a buffer, was just derived from the Ka expression. Or a Kb as well. Like you could have done it with Kb, which has OHs in it instead. And you don't have to memorize this. I'm just showing you. Okay, so we're going to do a practice problem. Here we go. Ethanoic acid. Oh, that stupid fancy word. This is acetic acid. Ethanoic acid is acetic acid. That's the fancy name for it. Okay, and I give you its pKa, which is a hint. If you see a Ka, pKa, the substance is weak. Okay? And I want you to find the pH of a solution that results from adding sodium hydroxide to ethanoic acid, which is acetic acid. I need you guys to get really good at writing net ionic equations. What I'm doing right now is I'm skipping the long part where you write out the whole reaction, you split apart everything you're allowed to split apart, you cross out the spectator ions, and then you write what's left over. I am literally jumping to straight what's left over. If you can't do that, that's okay. You need to do the whole process though. We're working with net ionic equations. So what I do is I go, okay, ethanoic acid is acetic acid. It is a weak acid. So how do I write it? I write it intact because weak species do not ionize significantly enough to break them apart when you do net ionics. And then I say, so plus. Sodium hydroxide is a strong base. Which part of it makes it the base? The sodium or the hydroxide? Hydroxide, right? I get rid of the sodium. Why? It's going to be a spectator ion. Weak acid, strong base. What kind of reaction is this? Acid and a base is called neutralization, right? What should we get? Acid, base, salt, water. So who's my salt? Well, remember, acids donate hydrogen ions and bases accept them. So you get CH3COO minus after it loses the hydrogen, and the OH takes it, so you get HOH, also known as water. And you go, how is acetate a salt? Well, because that would have been sodium acetate. Where's the sodium? It doesn't matter. It's a spectator ion. Not there. Not participating in the reaction, so I'm not including it. Acid, base, salt, water. Okay? So this says it's a buffer problem, yet it's starting off as a neutralization problem. It's not a buffer problem yet. It's a neutralization chemical reaction problem. What do I need to do next? And this is where kids are getting stuck. Well, besides not being able to do this, what do I need to do next? You're taking two solutions and mixing them together. So what should I do? What happens when you mix two solutions, no matter what? But regardless of the fact they're going to react, what also happens before that? Dilution. Very, very good. Very good. Dilution. So what is that? M1V1, M2V2 for both species, for the acid and for the base. So let's see, who's given first? It looks like the base is given first. 0.040, 40 of it. The new volume should be 90 because 40 plus 50 is 90. And then you do it again for the acid. Okay, so we have these numbers, right? So, to recap, we have a neutralization reaction. A weak acid and a strong base are reacting to give us salt and water. We had to dilute them because they got mixed together. So dilution does occur. We have not yet reacted them, but we need to. This is chemical reaction. So the question becomes is now what type of problem is this mathematically? Not chemically, it's an acid-base problem, chemically. But mathematically, what type of problem is it? Limiting reactant. Why? You know amounts of both reactants. So I'm going to go over to the next slide. I'm going to just rewrite my reaction out. I'm just rewriting the net ionic reaction out. And ice charts are just a nice tool to organize limiting reactant problems as well as to do equilibrium problems with solutions. So the acetic acid was 0.04166 something. And then the hydroxide was 0.017777777. Okay, no acetate. Who cares about water? And again, it's a limiting reactant because I have amounts of both reactants. So they're in a 1-to-1 ratio, so whoever you have the least of is your limiting. That would be the hydroxide. I have the least of the hydroxide, so you lose all of it. And then you lose the same amount across the board. But you gain product, right? Because products are being produced. And so this is 0. Now I'm keeping all the numbers in my calculator, okay? Okay. Let's flash back. What did the problem ask us to do? It said find the pH, right? So the first way we ever learned to find pH was pH equals negative log H. So in order to do it that way, you have to have H plus or H3O plus, whatever you want to call it, concentration. Do you, or do we, have H3O plus right now? Or H plus anywhere? No. So that weighs out. So another cool way to find pH is if you know POH, you could just subtract that from 14 and get pH, which is like a nice little easy shortcut. So in order to know POH, you have to have OH. Do I have OH left in this one? No, it's gone. So I can't do that. So what do? There's only one other pH equation, right? Henderson-Hasselbalch. What does it look like? It looks like this. Now, the conjugate goes on the top, so that's acetate. And the weak species goes on the bottom, so that's acetic acid. And the Henderson-Hasselbalch equation is the equation of a buffer, which means there's a buffer in here, and we'll talk about that in a second. pKa was given in the problem. If you go back, I gave you pKa. It is 4.75. So the pH equals 4.75 plus the log of and let's see, 4.62. Uh-oh. What's happening? Four point 4.62, 4.63, 4.61. It's really going to depend on how you rounded. So what started out as a neutralization problem, an acid-base reaction, turned into a buffer because the neutralization produced salt. And you ended up with a weak substance and its conjugate present in solution, which is what forms a buffer. So the buffer was like a byproduct of the neutralization. The neutralization helped make the salt, and now I have weak species and salt in there. I've created a buffer from a neutralization reaction. Questions so far? Okay, we're going to try another one, but you're going to try this one on your own. Now, I need to warn you. This is going to be another buffer problem, right? But anyways, I gave you Ka. If you use Henderson-Hasselbalch, it does not have Ka in it. It has pKa. So you got to remember that that P means opposite the log. So pKa is opposite the log of Ka, just like pH is opposite the log of H. So you don't want to forget this right here. The other problem was easier because I just straight up gave you pKa. You're going to have to do a little bit more work to get pKa in this one. So I'm going to give you a little bit of time. I am going to go over it, but I want you to see, based on what we just did, if you can try to work on this one. All right. So we should have this equation. Weak acid, strong base, salt water. And then again, dilution happens because you're mixing two solutions. So this is going to be the diluted concentration of the sodium hydroxide, and this is going to be the diluted concentration of the methanoic acid. Are there any questions so far? Final volume is 48.9 because 23.9 plus 25 is 48.9. Okay, so I'm just going to transfer this over to the next slide. So the methanoic acid was 0.05122 something, or 112 something. And the sodium hydroxide was the 0.04888875 something. Nothing at the beginning. Who cares about water? Again, 1-to-1 ratio, limiting reactant, because I have both reactants. Hydroxide is the thing I have the least of, so I'm going to lose all of it to not have any at the end. So this is like 0.0022494 or something. Okay, and now I gain the 0.048875. Again, I'm just trying to keep as many numbers as I can because you're not done with the problem, so you want to try to avoid rounding. Writing it down isn't a big deal. If you just keep the numbers in your calculator, you can just do it that way. Now, again, I don't have H plus, so I can't find pH the normal way. I don't have OH minus, so I can't find POH, but I do have a weak species in the presence of its conjugate, which means I have a buffer. So I can use the Henderson-Hasselbalch equation. pH equals pKa plus the log of, now the conjugate goes on top, which is this guy, and the weak goes on the bottom. And again, I didn't give you pKa, so you had to do a little bit of work to get the pKa. I think the Ka is 1.6 times 10 to the negative fourth. So to get pKa, you take opposite the log of Ka, which is opposite the log of 1.6 times 10 to the negative fourth. And it's like 3.79588 or whatever. So pH equals 3.79588 something something plus the log of the 0.0. Okay, and I'm pretty sure it's 5.133, 5.132, 5.134, whatever. So again, an acid-base neutralization reaction created a buffer. This will never happen with a strong acid, strong base reaction. Buffers are not produced during strong reactions. Okay. Now, I did tell you that you could use the Ka expression to do this. So if you feel comfortable with the Henderson-Hasselbalch, you don't need to listen to me right now. Okay? how would that work? Well, this is how it would work. I'm not going to change anything up there, because the Henderson-Hasselbalch is derived from a Ka expression. Well, you go, well, what's the Ka expression based off of? Well, it's based off of the weak acid, right? So what does a Ka expression look like for the weak acid? It looks like this, or a reaction. And this is why this throws people off, is because I'm putting water in here. Well, that's because a Ka expression is not written for a chemical reaction. It's going to be written for the weak species. So HCC. All right, and it would look like this. Okay, products over reactants. And then I gave you Ka, so that goes right here. Okay, and you know these guys. They are right here and right here. So I can plug them in. So the conjugate is 0.048875 something something. And the weak acid is 0.002249. And guess what I can solve for? The H3O plus. Well, if I know the H3O plus, I can find the pH because I can just take opposite the log of it. So let's find out what H3O plus ends up being. This number actually comes out a little bit different. So you would take 1.6 times 10 to the negative fourth, multiply by this number right here, and divide by that number, right, cross multiplication. And that gives you H3O plus. Well, if you know H3O plus, you can find pH. The H3O plus comes out to be, doing it this way, 7.36245 times 10 to the negative 6. Well, if I take opposite the log of that, I'll get pH. Now, oh, it does come out better. It is. It's 5.133 actually. So I was just trying to show you that you could use a Ka expression for the weak species, the weak acid. If this was a weak base making the buffer, you would use a Kb expression for it if you want to do it that way. But if you feel comfortable just plugging into the Henderson-Hasselbalch, there's no reason you can't do that. They're derived from one another. So it doesn't matter which way you do. I'm just showing you there are two routes. Wow. You guys got to unmute yourself to tell me I'm muted. At least I recorded it, so I'm just showing you that this is how you could use the Ka expression to solve for the pH, and you get the same exact answer. Sometimes it comes out slightly different, but that's not a big deal. Okay. Now, we're going to decide, this is a multiple choice question, which of these will produce a buffer? So if you look at these, we have acids and bases. There's no like weak substance and a salt, so that's not going to be any of the options. So we know that in order to produce a buffer from an acid-base reaction, one of the species has to be weak and the other one has to be strong for the sake of this class. So A is out. You are never going to produce a buffer from a neutralization between a strong base and a strong acid, ever. Bye-bye. So now B, C, and D are all the same base and all the same acid. It's sodium hydroxide, strong base, and acetic acid, weak acid. So on the next slide, I'm just going to write out, why don't you try to write it out, the net ionic equation for sodium hydroxide and acetic acid. How do I write a strong base sodium hydroxide? I write it as OH minus. I get rid of the sodium because it's a spectator ion. How do I write the weak acid? I write it intact because weak substances do not ionize well. So the base accepts a hydrogen, the acid loses a hydrogen, so you get this. All right. Base, acid, salt, water. Now, in order to be a buffer, what do we know we need to have? To be a buffer, we need to have a weak species, and we also have to have its conjugate present. You need both parts to be a buffer, or you're not a buffer. So I'm going to set up an ice chart because they gave me molarities. And the first molarities they gave me were equimolar. Same concentration of acid and base. Right? So they're both perfectly limiting, right? Because they're a 1-to-1 ratio. Okay. Do I have a buffer? I mean, I have the conjugate, but like this guy is missing. So I don't have a buffer. There's not a buffer. And I'm going to go into further detail. This is an acid-base neutralization reaction, right? Where does this happen in a titration? This is a special point during a titration. What is it called? Equivalence point. When the acid and the base are equal, you are at the equivalence point. I'm going to go further. This is not related to this problem. If I asked you to calculate the pH of this system, this is really important. I don't have OH. I don't have H. I also don't have a buffer. What do you have to do next? What happens at the equivalence point of a weak strong? If this was strong, the pH is 7. But in a weak strong, something happens. The salt undergoes hydrolysis. That's what you would have to do to calculate the pH at this point. Okay, either way, it's not a buffer, so B's out. All right, new concentrations, 0.02 and 0.01. So let's go back to that. So the base changed to 0.02, and the acid stayed as 0.01, no salt in the beginning. So it looks like the acid is the limiting still, because you have the least amount of it. You do not have a buffer. The weak and its conjugate is missing the weak. You could straight up find POH right now because you know OH. It's 2. This is 1 times 10 to the negative 2, so POH is 2, so pH is 12. But I didn't ask you. Either way, it's not a buffer. I'm missing a component of the buffer. All right, so the last one swaps the hydroxide and the acetic acid. The hydroxide is 0.01 now, and then the acetic acid is 0.02. So let's go back to our ice chart, and we'll swap their values. This is 0.01. This is 0.02. And now this is my limiting reactant, so I lose all of it. So I don't have any left. But 0.02 minus 0.01 is 0.01. Oh, I now have both components needed for the buffer. I have a weak substance present with its conjugate. So this is a buffered system. Okay. So a buffering capacity or a buffer capacity is just the ability of a buffer to neutralize an acid or a base. So a buffer has two parts. It has an acidic part and a basic part. If you add an acid to a buffer, it will react with the basic part of the buffer. If you add a base to a buffer, it will react with the acidic part of the buffer. The more concentrated your acidic and basic parts of the buffer are, the better the buffering capacity is because you have more of it. The more of it you have, the better of a buffer it can be. Okay? And in general, really good buffers have similar amounts of the acid and the basic part. They don't have to be identical, but just like similar. So if you have like part of a buffer that's 0.1 molar and then the other part is 0.0001 molar, it's not going to be a great buffer. All right. Now, this concept right here is going to be, or this thing is going to be conceptual. Actually, I'm going to skip this real quick and I'll record this when we're done. Okay. So we need to show how a buffer works. So let's look at this. Ammonia, NH3. And ammonium chloride is a buffer. So here's the thing. It's not the chloride that's important. Ammonium chloride is this. Which part of this is going to be helpful for the buffer, the chloride or the ammonium? The ammonium, right? Because they're conjugates of one another. Who cares about the chloride? Well, ammonia is a base. It's a weak base, which makes this an acid, a conjugate acid. So if you're going to throw hydrobromic acid, strong acid in there, and I'm going to represent strong acid like this, you can also represent it like this. The acid is going to be neutralized by the basic part of the buffer. This guy. The H plus and the NH4 plus aren't going to do anything. They're going to like see each other and be like, hey, what's up? We're the same kind of thing. But the basic part of my buffer will neutralize the acid. So when you go to write out the reaction, it looks like this, H plus plus NH3. Okay, these two mean the same thing. And then you go, whoa. So the acid ate up some of my base, but then it produced, through that neutralization, another part of my buffer. So the neutralization reaction helps you make more buffer. That's why buffers are so great, because when you add a little bit of acid or a little bit of base, you make the other component of the buffer. So you can just go back and forth and back and forth. Now, obviously, if you add way too much concentration of something, the buffer will be wiped out. This can't last forever, but that's what happened right here. So now I have this buffer, and instead I'm going to add potassium hydroxide. What am I trying to tell you I'm adding? Hydroxide, strong base. Which part of the buffer, this is my buffer right here, the ammonia and the ammonium chloride. Where's the chloride? Who cares? Okay, here's my buffer. Who's the base going to react with in the buffer? The acid. The base and the base aren't going to do anything. They're just going to see each other and be like, hi, we're the same thing. We have no interaction with one another. So the hydroxide is going to react with the acidic part of the buffer. That's the ammonium. And what do you get? Well, you get this. Oh, look. I used up some of the ammonium, but then I produced ammonia. I just reformed part of my buffer. So like while the neutralization eats up some of the buffer, it also produces the other part of the buffer. And so you can go back and forth until your buffer is completely used up. All right, we're going to try another one. Show how a buffer from acetic acid and potassium acetate would effectively neutralize these two substances. So acetic acid, that must be my weak part of the buffer. Why? Because it's a weak acid. And you can write acetic acid, the HC2H3O2. You can write it that way if you want. Acetic acid. Potassium acetate. Who do I care about in the potassium acetate? Is it the potassium? This is a salt, metal, nonmetal. Or I'm sorry, metal polyatomic, I should say. It's the acetate that's going to be the helpful part of that, right? So this is the acidic part of my buffer. This is the basic part. Where did this guy come from? This guy came from potassium acetate. So I'm going to add HCl. It's a strong acid. So in essence, what they're telling you is you're adding H plus ion. Or you can call it H3O plus ion. I don't care. Which part of the buffer will the acid react with? The basic part of the buffer, right? So that's this guy. Or if you did it this way, with the hydronium ion instead, you would just get this and water. Okay. How about the base? So I know I have a minute, so I'm just going to finish up right here. Well, the base is hydroxide, sodium hydroxide, but it's specifically this part that's the base. It's going to react with the acidic part of the buffer. That's this guy. Okay. All right. So similar type of problem. Hydrobromic acid. So in essence, they're saying H plus strong acid. Where's the bromic, Br minus? It doesn't matter. Okay. That's not part of this system. It's added to a buffered solution containing acetic acid. So who's acetic acid? That's CH3COOH. And then what they say is, and it's salt. So maybe it's sodium acetate, potassium acetate, lithium acetate, something with acetate. So they're not specific. So it's kind of your job to know that this is the salt of acetic acid. Okay. And they want you to do the net ionic equation. Well, luckily, that's what we've been doing. So the acid, so this is acetic acid. This is its base. This is the acidic part of the buffer. This is the basic part of the buffer. The hydrogen is going to react with the basic part of the buffer. So the net ionic is H plus, right? We get rid of the Br minus. And then the salt looks like this. To make okay. Now, you could be writing it like this instead of H plus. Either way is acceptable. This one would just end up with water as well on the other side. This thing loses a hydrogen, this thing takes the hydrogen. Okay, so let's try one more. Sodium hydroxide, so they're telling you OH minus, NaOH, which is OH minus, is added to a buffered solution containing hydrofluoric acid. Remember, HF is a weak acid. And it's salt. Now, they don't tell you who the salt is. So what am I going to need to have? I'm going to need to have the fluoride ion, right? That's the conjugate of HF. So maybe it's sodium fluoride, potassium fluoride, lithium fluoride. I don't care, fluoride. Anybody fluoride, okay? But in essence, it's F minus that we care about. That's the basic part of the buffer. So this is the weak acid. This comes from the salt of the weak acid. And now this time I'm adding a base though. So the base is going to react with the acidic part of the buffer. So that would be HF. And this guy just floats around and doesn't do anything. OH minus. The weak acid part of the buffer. The base being added. Acid, base, salt. Right? Donates a hydrogen, accepts a hydrogen. Water. All right. Okay, sometimes they ask this concept or this question conceptually, not mathematically so much anymore. So they want to know when is pH less than pKa when it comes to comparing, this is for a buffer, comparing the buffer, and we're comparing the salt in the buffer and the weak species in the buffer, whether it's a weak acid or a weak base. So we want to know who we have more of when this happens and who we have less of, right? Because the buffer consists of these two parts. So in order to do this mathematically, we kind of need to talk about the Henderson-Hasselbalch equation. Okay, the salt is on top, which is the conjugate, and then the weak species is on the bottom, always. Okay. So because we're doing pH and pKa, I'm going to write this as acid because H means acid, A means acid. We could do this for a base as well, but this equation would change. So when the salt and the acid are equal, this number is 1, and the log of 1 is 0. So when you have the same amounts of salt and acid, conjugate and acid, pH equals pKa. Okay. However, if you plug fake numbers in, I want to have less salt concentration than I do acid. I'm just plugging fake numbers in there. Lower concentration, higher concentration. So right now, my salt is lower concentration than my acid. So if you take the log of a number less than 1, and when I say less than 1, I'm not talking about negative numbers. I'm talking about decimals like 0.9, 0.8, 0.01, 0.00001. You will notice that this term, the log of 0.1, the log of 0.2, the log of any number less than 1 but not negative, okay? This term, though, comes out to be negative. So if it's negative and you add it to pKa, pH drops. So this is when pH is less than pKa. When you have less salt in your buffer than you do acid. Salt or conjugate, you can call them the same, okay? Which of course is going to mean the opposite of this is true. So Henderson-Hasselbalch again. So we have the salt on top, and we have the acid, in this case, on the bottom. And now I'm going to make my salt more concentrated. I'm going to put this number in for it. And I make my acid less concentrated. I'm just throwing in fake numbers, okay? Well, this is a number greater than 1. So we know that the log of 1 is 0, and less than 1 gives us a negative value. But greater than 1, which would be this would be the log of 2, right, gives us a positive value for this term. So right now I have the fact that my salt is more in concentration in my buffer than my acid. So if this is a positive, and this has to be a positive, your pH is actually going to go up. So your pH will be more, because we're adding this term to your pKa, than your pKa. So the pH is greater than pKa when your buffer has more concentration of salt than it does of acid. You can also call this conjugate, salt or conjugate. Right? HF. H plus, F minus. Acid, conjugate base. This is a salt. Sodium. Salt. The conjugate is a salt. Okay?